Okay, I made the claim in class that you could prove that if you have a collision where two objects stick together, so here's M1, here's M2, I made the claim that if you have a collision and you end up with a final object, M1 plus M2, I made the claim that you can prove that energy is not conserved. And I said that it was algebra E, so I didn't want to do it in class, but here I am. I'll do it here for you. There are two ways to do this problem. One is a little easier than the other. So I'm going to start with the hard, ugly way. And then when you suffer through that, you'll appreciate this trick that you can use, which makes it easier. So let's set up our conservation of momentum. So P initial equal P final. If it's a sticking collision, this means that M1 V1 plus M2 V2 equals M1 plus M2 times V, whatever V is. Okay. And so these are vectors. Of course, we're in one dimension here, but I'm putting vector arrows above them just to say that things can be positive or negative. Okay. We do have some things that need to be true though. Like for example, V1 has to be greater than V2. Because if that's not the case, if V1 is moving to the right and V2 is moving to the right and V2 is moving faster, you don't get a collision, right? If V2 is negative, that's okay. It means it points to the left and you'll still have a collision. So this is true. We also want to make the demand that the masses are greater than zero. So that's another thing that we'll want to say. Okay. All right. Anyway, so what this tells us is conservation of momentum, that the velocity, the final velocity is m1 v1 plus m2 v2 divided by m1 plus m2. Okay, so let's look at the kinetic energy final, Ke final, and that is 1 half m1 plus m2 times v squared. Okay, and then that is 1 half m1 plus m2 times m1 v1 plus m2 v2 divided by m1 plus m2 quantity squared. So I'm going to start dropping the arrows here over the vectors and just say that, look, the v's can be a positive or a negative number, and that's kind of what the arrow meant in the first place. So they're just cumbersome. I'm going to stop writing them. Okay. So the question is this equal question mark to the initial kinetic energy, 1 half m1 v1 squared plus 1 half m2 v2 squared. Okay, so we will follow this through to its conclusion and see if we can, we'll assume it is equal, and if it is, great, and if it's not, not. Feel free to fast forward or watch in triple speed or whatever you want to do, because this is just going to be, actually, you know what? Okay, boom, a little movie magic for you. You can spend as much or as little time looking at this as you like. The point is that if it were true that energy is conserved, you'd have to get the case that V1 equals V2. And remember, signs are important. So that means that your original setup would look like this. But how on earth are these things ever going to crash into each other if they are both moving at the same speed? The answer is they can't. The only way for energy to be conserved in this case is if V1 equals V2, and you simply don't get a collision if that happens. Okay, so you can see this algebra is pretty monstrous. Pretty monstrous. Here's the easier way to do it. You say, okay, well, I'll start out with a block moving to the right with a speed v. This has m1. And I'm going to say that the other block has to be stationary. And you might say, well, that just makes the problem easier. You're not doing it for the general case. But, remember that we can always shift how we view our coordinate system. In other words, I'll just look at the relative speed between the two. Or if M2 had some speed, if M2 were moving to the right, say, then I'm just going to stand on top of M2. And then from my point of view, M2 isn't moving at all. Relative to me, M2 is at rest, and M1 is the only one moving. And you might say, well, that's not what's happening. But, Newton's laws don't depend on reference frames. The laws of physics are the same. And so, however momentum is conserved in one frame, it's got to be conserved in other frames too. If energy is conserved in one frame, it's got to be conserved in others. And so I'll just shift my reference so that this is now the relative speed between the two. And then this problem becomes cake. So check out how much simpler this algebra becomes. My initial momentum, P initial, is M1V. There's no other momentum. This becomes M1 plus M2 times V final. So V final becomes M1V over M1 plus M2. Okay. Now, let's look at the kinetic energies again. So the final kinetic energy, 1/2 M M1 plus M2 times V final squared. So that's 1/2 M1 plus M2 times M1 squared V squared divided by M1 plus M2 squared. And that's equal to my initial kinetic energy, which is 1/2 M1 V1 squared. So this is much, much easier to do the algebra. I'll still pause and do movie magic anyway. So that's my movie magic. You can spend a couple seconds looking at that if you want, or not. The conclusion we get, though, is that this product is 0, which means either M1 is 0, M2 is 0, or V is 0. Either way, you have no collision. If V is 0, nothing collides. If either of the masses is 0, there's nothing to collide with. So we'll consider this proved that in a sticking collision, it is impossible to conserve energy. And I'll show you this in case you watch all the way to the end. Whenever you show something, you can put a box at the end. That means that you proved what you wanted. You can put QED, which is quadratus demonstratum. That's pretty fancy. And then this is my favorite, W to the 5th, which was what we wanted. All right.